In this video, we're going to talk about the property of carboxylic acids. We'll go to talk about the melting point, the solubility, and then go on to do some of the reactions of carboxylic acid and do some balance symbol equations. Now, carboxylic acids do hydrogen bonding. Okay, so let's have a look at how that actually works with some simple carboxylic acids. So I'm going to draw the simplest carboxylic acid, which is methanoic acid. Only has one carbon, it's methanoic acid. Okay, and you can see our carboxylic acid group is this group here. Okay, now if that is the case and it's going to bond, it can do two types of hydrogen bonding. It can do hydrogen bonding with water, and there is your water molecule. And then what we have to do with hydrogen bonding, if we're going to get exactly the right marks in an exam, if we're drawing this, is to show the lone pairs. So I'm going to show the lone pairs on that oxygen. Okay, and the hydrogen bond's coming from this oxygen, so don't worry about doing lone pairs there. Okay, and then from that point, we can there say there is the hydrogen bond, but we can also do the dipoles. The dipoles are really, really important. So therefore, we've got a delta positive there. We've got a delta negative there. Delta positive, and you can even go as far over here, delta negative, if you want. Okay, but the most important dipoles are these two dipoles here. So we've got the lone pair of electrons, which is on the delta negative oxygen, which is attracted to the delta positive hydrogen. To get a hydrogen bond, you have to have a delta positive hydrogen, and the only way it can be delta positive is when it's bonded to an electronegative element, such as N, O, or F, or NOF. Okay, so that means here's your hydrogen bond, and what that does is it affects its solubility. So it will be soluble in water. Okay, simple carboxylic acids will be soluble in water because of this. As the chain length grows, it loses that solubility, but we'll talk about that in the next slide. So let's do this again, but then let's do it in terms of carboxylic acid doing hydrogen bonding with itself. So if you are watching this video, why don't you try drawing it before I do and see if you can beat me in terms of time. Now remember, the H must go to an O. So there I'm going to put an O, and then I'm going to put carboxylic acid again. There you go, drawing it like that. I'll do the same process. I'm going to put my lone pairs of electrons on. I'm going to put my dipoles on. So delta negative, delta positive, delta positive, delta negative. Okay, so I've got all of that. And then I draw my hydrogen bond in there. So we have a hydrogen bond which is drawn between two molecules of methanoic acid, as you can see here, and we have a hydrogen bond drawn between water and methanoic acid. This diagram shows that it's soluble in water up to a point, and this one shows that the melting point is going to be higher because hydrogen bonds are stronger than most other intermolecular forces in most cases. Okay, so which means that they're attracted to each other more highly, which means their boiling point and melting point is higher than other molecules with an equivalent molecular mass. If you want to go over that in detail or remind yourself of AS content, there is an AS video on intermolecular forces and relative strength of intermolecular forces, which I'd recommend that you watch. But this creates the higher melting point and this creates the solubility. So it's really important that you know that because of these stronger hydrogen bonds and can draw it. So now we can draw the hydrogen bonds. Let's have a look at how hydrogen bonds don't come into the solubility discussion when the chain lengths are longer. So at shorter chain lengths, you will get solubility. Let me show you an example of that. We've got this very, very long chain length over here, and that is the carboxylic acid that's in olive oil. And then we have this very short chain carboxylic acid, which is in vinegar. So this is ethanoic acid, and this is octadecanoic acid. So here, just to give you an example. So we've got our picture here, and in our picture, hopefully you've been to a restaurant that does this because it's actually really quite tasty and quite nice. Okay, is you have olive oil here, and then you have balsamic vinegar here. So over here we've got balsamic vinegar. And what they do in predominantly Italian restaurants is they mix those together on a plate, and then you get a bit of bread and you mix your bread in it, and it's actually very nice. Now the fact is, whenever you put it on the plate, you can see the olive oil, which is here, and you can see the balsamic vinegar, and they don't mix. Well, the balsamic vinegar, okay, has short chain carboxylic acid in, and it's an aqueous mixture. So this is an aqueous mixture with a short chain. So that means the acid is dissolved within there, okay, because it's a short chain, and hydrogen bonding allows it to be dissolved. And then on here, in the olive oil, we have this long chain. Now, the chain itself is hydrophobic. Okay, so it doesn't like water. So what it does, it disrupts the hydrogen bonding, gets in the way of the hydrogen bonding, and therefore stops that bonding having a large effect on solubility, which makes it insoluble. And that's why on the plate you can see that the olive oil and the balsamic vinegar don't actually solubilize, because the olive oil has the long chain and the balsamic vinegar has the short chain. And so basically water and oil don't mix, but the difference is this long chain, which stops the actual miscibility happening. We're now going to go on to reactions of carboxylic acid. I'm going to look at two to start off with: carboxylic acid plus a metal and carboxylic acid plus a base. This is really the same as saying acid plus metal or acid plus base. It's the same type of reactions you went over in GCSE, but let's put this over to the side, and then we'll draw out some different types of formula for you to try and help you understand. So the first one is methanoic acid. So I'm going to draw methanoic acid in full displayed formula. So there is methanoic acid. I've got our carboxylic acid group, got one carbon in it because it's meth, so that is methanoic acid. We're then going to add that to sodium, okay, and then that will react, and what happens is the acid acts like an acid and loses its proton, so loses its H, and the sodium replaces that. So, and we get a salt, and the salt we get is sodium methanoate. So there's your O, and then here is your Na. Okay. Now, also you're losing the hydrogen, the hydrogen. Okay, and if you think about this in simple terms, this is acid plus metal goes to a salt, and this is your salt, this sodium methanoate, okay, plus hydrogen, if you remember this from GCSE. So an acid plus a metal is going to be the acid plus a metal goes to a salt plus hydrogen. But you'll just now need to get used to drawing a different type of salt. It's where the hydrogen leaves and the metal replaces that hydrogen. And this is the simplest example. Now you can sometimes see it written with a minus here and a plus here, because this is an ionic bond. And it's really useful to know that that's an ionic bond, because that means that will have a higher melting point than this, because ionic bonds are stronger than intermolecular forces such as hydrogen bonding, permanent dipole-dipole, and induced dipole-dipole. Now, if that's the case, balancing it is a bit simpler because you can do it as a group. So, for example, here you've got one of your carboxylate, okay, and one of your carboxylic acid, but you've got one hydrogen leaving, and I've got two over there. So what I need to do is put two of these in, because I need two of these hydrogens. And if I put two of those, I have to make two of the whole of this. And that means I need two sodiums. So I balance it all like that. And that is your balanced equation for if you have a carboxylic acid plus a metal. Remember, it's an acid plus a metal goes to a salt, in this case sodium methanoate plus hydrogen. Let's go and do the next one now, which is a carboxylic acid plus a base, or an acid plus a base. Hopefully you remember that an acid plus a base goes to a salt plus water. Okay, so we're going to do 2-methyl propanoic, and let's do this time in structural to show you what it would look like in structural formula. So 2-methyl propanoic acid. So we've got prop, so that's 3. So this will be 3 carbons. So let's go to the next carbon, which is carbon number 2. Now on number 2 it says there's a methyl. So I need the 4 bonds to the carbon. So I'll put 1 bond to that C, 1 bond to the H, and then the CH3 is coming off in a bracket there. That means that CH3 is coming off that carbon. And then our third carbon, because it's propanoic acid, is there. And then we add that this time to calcium hydroxide, a little bit more complicated. But again, this is an acid plus a base, or plus an alkali, because an alkali is a soluble base. So we'll put the arrow here and then continue the products down the bottom. So remember, it goes to a salt plus water in this case. So the salt is going to do exactly the same thing. So I'm going to take my metal like I did in the first one, and I'm going to bond it to my carboxylate ion, which is this negative ion that's produced after this proton has left. So if I draw it again, there's nothing to stop you trying to do this before me. There's my carboxylate ion. We're going to draw it as an O- because it's lost its proton. Okay, and then we're going to put our calcium here. Now, but the difference is with this, the calcium is a 2+. So the calcium is a 2+. So you've got to make the whole formula. It's really easy with this one. It's easy because there is a minus charge on the O- and a plus on the Na. Because of that, they just cancel each other out. Quite simple. But with this one, the metal is a 2+. Therefore, to cancel out the 2+ charge, I need 2 of these, because I need 2 minuses to cancel it out. So what I do is I put that in brackets. Okay, and then I will get 2 of these. So the formula of that salt is going to be the CH3, CH3, COO2, and then with the calcium, it's 2+ as well. Now we said that was plus water, so you then plus water. Okay, and so we have that plus water. Now we're looking to balance. So we've got a balance. So if we try and balance, we've got 2 of these whole carboxylate ions. They come from this, therefore I must need 2 of those. Okay, and then I look to see whether everything else balanced. My hydrogen's balanced. Do my hydrogens balance? Well, I've got 2 hydrogens there. Okay, and I've got 2 hydrogens there because I've got 2 of these. So I've got 2 hydrogens coming off here. So in total I have 4 hydrogens. Now I've only got 2 hydrogens here, so I need to double that. So that's now 4 hydrogens. Okay, and there were 2 oxygens here. There's now 2 oxygen here, and it's fully balanced. So you need to get used to the fact that, one, you can do it in displayed, you can do it in structural, and also you can do it with metals that have a charge of 2+ and metals that have a charge of plus. You can also do it with metals that have a charge of 3+. If it was 3+, you would just need 3 of these carboxylate ions instead of 2. And that is how you draw these different formulas to do these acid-base and acid plus metal reactions. The next reaction is when you have carboxylic acid plus a metal oxide. That will create a salt plus water. So if we take that again over to the side, okay, and we're going to create our salt plus water. We've done displayed formula, we've done structural formula, we're now going to do skeletal formula from now on. So the propanoic acid has 3 carbons in it, so basically there's your 3 carbons. We're then going to turn it into our acid, and there you have your propanoic acid. Then add it to the magnesium oxide. There you have your magnesium oxide. Now, really important that you realise there, the magnesium is a 2 plus, the oxygen is a 2 minus. So if we then turn that into our products, again, it's going to lose the proton. You can see here the proton, it's an acid. It's going to lose the proton. This is going to act like a base. Okay, those protons are going to go to the oxygen and create water, and then the magnesium is going to form a salt with the propanoic acid. So the propanoic acid, as it normally does, loses that proton and turns into our carboxylate ion. You then have the magnesium. Remember that magnesium is a 2 plus because it's in group 2, it's lost 2 electrons. Okay, and we need to balance those charges, minus and 2 plus. So we put our brackets round and we need 2 of those, and that can be. Now you can draw this without the minus, without the 2 plus. As long as this balancing is correct down here, okay, you can do it like that. Or you can do it with the minus and the 2 plus. Both are correct. And then with the hydrogen and the oxygen combine to give our water. So we have got this propanoic acid, magnesium hydroxide. Let's just check it balances. We've got 1 magnesium, and we've got this whole carboxylic acid here, and there you've got the whole carboxylic acid again, but without the hydrogen. If we look at those hydrogens, we need those hydrogens to balance, and we need these propanoic acids to balance. Well, I've got 2 of my carboxylate, so that means I'm going to need 2 of these. Okay, and then that and that balances. Okay, my magnesium balances and my hydrogens balance, more importantly, because I've got 2 hydrogens here and 2 hydrogens here. And that is how you do a carboxylic acid plus a metal oxide going to a salt plus water. And it's a really common question, and now we've done it in 3 different types of formula, which is displayed, structural and skeletal. In our last example of reactions of carboxylic acids, we're going to look at propanoic acid plus sodium carbonate. This is literally an acid plus a metal carbonate, which hopefully you'll know is going to a salt plus carbon dioxide plus water. And we're going to do exactly the same process as we've done before. So let's move this over to the side. Okay, and then let's do it in our skeletal formula. So our skeletal formula again, there is our propanoic acid. Propanoic acid is then going to react with our sodium carbonate. Now the sodium is a plus and the carbonate is a 2 minus. So the carbonate is a 2 minus, sodium is a plus. So we need 2 sodiums to balance out the 2 minus. Then that becomes our carboxylate again. There's your carboxylate, and the metal will then create this sodium salt. That's the case, the minus and the plus balance, and we get CO2 and we get H2O. We then need to balance the entire thing. So again, let's look at the sodiums to start off with. You see 2 sodiums, you see 1 sodium. So I need to put a 2 in front of this. That means I now have 2 of my carboxylate ions, which come from 2 acids. And then I have a look at the hydrogens. Do the hydrogens balance? So I've got 2 hydrogens here. I've got 2 hydrogens here. I've got 3 oxygens here. 1, 2, 3 oxygens here. So the whole thing balances. Now, again, if you've watched the video, why not go back through the video, try and do all these before I go through the answers. And if you have gone through all the answers and done them yourself and you've got them right, well done.